Math 111Z, and this is section 2.3. Our goals are to define a function, evaluate functions as a certain endpoint, interpret a table or a graphical representation of a function, and then define the domain or range. All right, so first of all, when you're talking about a function is a set, by definition. A function is a set of ordered pairs. Such that for every x, often called your input, there is exactly one y, known as your output. We often talk about functions in terms of like a function machine. If you put a value into a machine and it changes that value in some way, I put 3 in, I get a 7 out. Then 3 is my input and 7 is my output. And every time I put 3 in, I have to get 7 out. If sometimes I put 3 in and I get 5 out, then the machine's not functioning. In order for this to be a well-defined function, when you put something in, if I put a 3 in, every time I put a 3 in, I should get 7 out. That doesn't mean that sometimes I could put 4 in and also get a 7 out, but every time I put 4 in, I need to get a 7 out then, once it's defined. We will often think of this also as like a map problem. So if you have like, this is your inputs, your domain, and you map it over here to your range, also your outputs, and you have this point goes over to this point goes over to this point goes over to this point. I often tell people to think of the domain as people and the range as places. So, for example, Sam can go to the movies, and Kennedy can go to the store, and Henry can go to his friend's house, and that's all works out perfectly fine. We can also have Millie can also go to the movies. 2 people can go to the movies. But what you can't have is one person go to 2 places at the same time, right? We can't have Millie at the movies and the store at the same time. So in order to be a function, it has to have this relationship that for every input, there's exactly one output. So let's, how do we check to see if a function? Basically, all I have to do is look down, like there's different ways that a function can be represented, first of all. It can just be listed as a set of ordered pairs. So this could be a function. Here's another example. Here's another example. Okay, so some music outside or something. All right, so this relation A is a function because every x, there's no repeats on the x's and they all go uniquely to a y. b is also a function. Even though 3 goes to 6 and 5 goes to 6, there's no repeats on the x's. C is not a function because here 3 is assigned to 6, but here 3 is assigned to 9. So this right here means it's not a function. So you can just list ordered pairs to describe a function. You can also have an input-output table. So here is a input and output table. Right. Excuse me. This is a function. Even though they all go to the same place, there's not one of the inputs trying to go to two different places. So that's one way. You can do a map, a graph. They had just a finite number of things, like we just did. You can also do an equation. So something like y equals 2x plus 5. That is an example of a function. And this is an infinite function because infinitely many numbers can come in and go out. So like it's an infinite function. These are discrete functions. This is continuous and infinite. There's also something that we've talked about probably before. It's called function notation. Instead of calling this y, because I could have lots of different functions called y, right? Instead of just calling that y, I might call these all different letters. And the nice part about this type of notation is that I can then use this notation to show what my input and output is. So if I wanted to find f of 4, that would be 2 times 4. Wherever I see an x, I put a 4, plus 5, which would be 8 plus 5, which is 13. H of 4 would be 4 squared, which would be 16. G of 4, wherever I see an x, I'm going to put a 4, would be the square root of 4, which would be 2. Now, in each of these things, this ordered pair is an element of my function. So 4, 16, 4, 2. This is a point on the graph of G. This is a point on the graph of H. This is a point on the graph of F. So graphing is another way that I could display my function. So let's say I had f of x equals x squared plus 3. If I wanted to graph that, I'd have my 3 here. I'd go up 3, over 1, up 1, up 1, over 2, up 4. And I would have my parabola looking like that. Now this is a function. One of the ways you can tell it's a function is it passes something called the vertical line test. If I can draw vertical lines anywhere on my function and it only touches the graph once, then it's a function. See? Only touches once, only touches once, only touches once, only touches once. Right? That's different than a horizontal line, obviously. It touches twice. But a horizontal line is not necessary for a function. Vertical lines are. We've been working with graphs of circles, like something like this. So we know how to graph this now. This is a circle with the center at -3, 0, and has a radius of 3. There's my circle. That's a terrible circle, but you get the idea. all right? This is not a function because when I draw a vertical line, it touches my graph twice, so it's not a function. Let's have the function called f of x is equal to x squared minus 1. And it wants me to evaluate the following things: f of negative 2, f of 1/2, f of x plus 1, f of m. Let's talk about these, right? So f of negative 2, wherever I see an x, I'm going to put negative 2. Negative 2 squared minus 1. Negative 2 squared is 4 minus 1, 3. F of 1/2, wherever I see an x, I'm going to put the 1/2. So 1/2 squared minus 1. That's 1/4 minus 1, which is negative 3/4. X plus 1, wherever I see an x, I'm going to put an x plus 1. Right? So if I FOIL that out and collect like terms, I'd get x squared plus 2x. So that's how that one. M, wherever I see an x, I'm going to put an m. So this would just be m squared minus 1. Okay. So that is how you can simplify those functions. Sometimes your function will be given to you in pieces. Consider the function h of x that has 3 pieces. It's a straight line at 1 if x is less than 0. It is another line, but slanted, between 0 and 2. And it's a straight line at negative 3 if x is greater than 2. So what does this look like? Oops. Right, we have my line here. I'm going to put some negative 0. So we will have a work day tomorrow, so we'll have lots of time to finish up any homework that you need to get done and ask any questions that you need.